Hi everybody and welcome to video number 14 in the solutions series. So here we'll be discussing about depression of freezing point. So at freezing point what happens? Of a substance, if you take a pure substance, the solid phase is in equilibrium with liquid phase. Okay. So thus freezing point may be defined as a substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to vapor pressure of the substance in its solid phase. So a solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent. Now what do we know when a non-volatile solid solute is added to the is added pure solvent, solution forms, and the solvent, this decreases the vapor pressure. Because of this, vapor pressure of solvent decreases, right? Now the lowering of vapor pressure of the solution causes lowering of freezing point compared to the pure solvent. So let us understand diagrammatically what is happening. क्या हो रहा है? Now this is the pressure, temperature. Now what is the phase diagram of a pure compound or one component system? It will be something like this, right? like this. So this is your solid phase, liquid phase, and your vapor phase. Now what we are trying to tell is that there is a point at which the liquid and solid are in equilibrium. Okay, this is that these are the temperature and pressure variables. Now when you add a solute, now when you add a solute, what happens is your vapor pressure of the liquid, so this is your original curve. Okay, vapor pressure curve. What happens when you add a solution? The curve decreases like this, right? See, now if this was your, this temperature was your freezing temperature of a pure solvent. Now there is a depression, which means at this point where the solid and the liquid is in equilibrium, there is a depression freezing point. So this is your new TF. Okay, let me draw it again here. Okay, see, this was the original freezing point. This is vapor pressure, and this is your temperature. So this was your original freezing temperature. Now when you add a solute, what happens is the vapor pressure decreases and therefore meets the solid curve slightly low at a lower temperature. So this is your new freezing temperature. So this much is a decrease in depression in the freezing point that has occurred. So for dilute solutions, experimentally it has been found out that experimentally it's been found out that delta TF, that is a change, the decrease in the freezing temperature is directly proportional to the molality of the solute, and delta TF is equal to KF M2, where your M2 is weight of 2 divided by molar mass and weight of, so here 2 represents solute and 1 represents solvent. So M2 Kf into W2. So this Kf, before we proceed here, so Kf is called freezing point depression constant. Constant or molar depression constant or cryoscopic constant. Cryoscopic in Greek means freezing measurement. Okay. Now if we know this, we know the depression freezing point, we know Kf, you know weight of 2, you know the weight of 1, and you know the molar mass of the solvent. So what you can do is you can calculate the molar mass of the solute. So molar mass of the solute can be calculated, which is equal to Kf I made a small mistake. This is not M1. This has to be your 1000 because it's molality. Molality is number of moles per kg of solvent. So your M2 can be calculated. What is Kf here? So Kf is equal to R into M1 into T freezing star T freezing star square into 1000 into delta H fusion, where R is gas constant, M1 is molar mass of solvent, F star is freezing temperature, pure solvent, the fusion is enthalpy of fusion of substance. Okay. So this is your heating. Now so this is in terms of molality of solute. In terms of mole fraction of solute, your delta Tf is given by K into x2, where K dash is RTF square by delta fusion. Okay. So this also is good in terms of mole fraction of the solute. Previous one was in terms of the molality of the solute. So that was your depression of freezing point. Thank you.